Hi, let's talk about three dimensions. We're used to two-dimensional coordinate system, also called the Cartesian coordinate plane, where we have two variables, x and y. This is flat, two-dimensional. What if we would like to study three dimensions? Well, we add a new variable z, and we can plot a three-dimensional coordinate system. It's hard to represent this in a two-dimensional surface, but we can envision this in 3D. Now, how do we label these axes? One of them is x, one of them is y, one of them is z, and it's a little counterintuitive at first. This is the x-axis, this is the y-axis, this is the z-axis. Of course, it doesn't really matter how we choose to label the axes, but this is the standard practice. We get this labeling from something called the right-hand rule. My apologies for the poorly drawn hand, but we can envision taking our right hand, pointing out the index finger, pointing the middle finger at a 90-degree angle, and then pointing the thumb straight up in the air. The index finger points in the positive x direction. The middle finger points in the positive y direction, and the thumb points in the positive z direction. If we can remember this labeling, we can remember the standard way for labeling three dimensions. Let's talk about some basic three-dimensional objects. A point in three dimensions has three coordinates, x, y, and z. For instance, we could have a point such as 3, 2, -1. A plane has an equation of the form a constant times x plus another constant times y plus a constant times z equal to some fourth constant. For example, we could have 5x minus 3y plus z equal to 2. That is the equation of a plane. A sphere in three dimensions has an equation that is analogous to a circle in 2D. X minus x1 squared plus y minus y1 squared plus z minus z1 squared equal to some value r squared. Here, the center of this sphere is at the point x1, y1, z1, and the radius of this sphere is r. It's difficult to sketch these sorts of objects on a flat piece of paper, so let's envision this in a three-dimensional graphing system. We will use GeoGebra. If you go to geogebra.org/3D, you can find a free online three-dimensional graphing system. Here's what it looks like. We have the x-axis, the y-axis, and the z-axis given by the right-hand rule. And let's try in some three-dimensional objects. A point we could sketch such as 3, 2, -1. If we look at this point, we can see that it goes 3 in the x direction, 2 in the y direction, and vertically down 1 in the z direction. Let's draw a plane. 5x minus 3y plus z equals 2. There's an example of a plane in three dimensions. Let's take a look at a sphere. Let's have a sphere centered at our point with a radius of 2. To get this, we take x minus 3 squared plus y minus 2 squared plus z minus minus 1, so plus 1 squared equals 4. This is a sphere centered at the point 3, 2, -1 with a radius of 2. Let's take a look at one more three-dimensional concept. Let's talk about distance in three dimensions. Suppose we have 2 points, x1, y1, z1, and x2, y2, z2. To get from one point to the other, we can imagine going some distance in the x direction, and then some distance in the y direction, and finally, some distance in the z direction. The distance in the x direction is the difference between the x coordinates, x2 minus x1. The y distance is the difference between the y coordinates, y2 minus y1. And for the z direction, we have z2 minus z1 as the vertical distance. We want the distance straight between these 2 points. We can find that using the following equation. This distance, we'll call it d, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. This equation essentially is a generalization of the Pythagorean theorem. This is the Pythagorean theorem in 3 dimensions. And this is how to find the distance between 2 3-dimensional points.